Hello, in this video, we are introducing the idea of the limit comparison test, which is, in general, a more forgiving test for most cases than the direct comparison. It still has its restrictions. Our sine squared example in the previous video is actually one that we can't easily use the limit comparison test on. But the limit comparison test kind of rules out some of these issues we have with the direct comparison test. So the direct comparison test has these problems that when I'm comparing my two sequences, if my inequalities are backwards from what they're supposed to be, the direct comparison test just completely fails to work. So what do we do when that direct comparison test completely fails to work? This is where the limit comparison test comes in. So the limit comparison test starts out the same as the direct comparison test. It says, suppose I have a series, or two series, an and bn, that have positive terms. This means our first step of our process is the same as it was before, and that is checking that our series has positive terms. Then, if we look at the limit as n goes to infinity of an over bn, and this comes out to some number c, where c is positive and finite, meaning 0 is less than c is less than infinity, then the series an and the series bn either both converge or they both diverge. Phrasing I use is they do the same thing. Because what this limit is telling us is if we're coming out to a limit that's just a number, that's not 0 and it's not infinity, that means as the terms go farther and farther, as our terms keep going off to infinity, they're basically the same terms with some ratio between them. Like the sequence an is the same as the sequence bn, just multiplied by 2, or just multiplied by a fifth. And we know for series that if we just multiply by a constant, then that doesn't affect whether this converges or diverges. So what it's saying is these sequences are basically doing the same thing, maybe off of each other by a constant in general. And so if that is true, then the two series have to do the same thing. Either they both converge or they both diverge. So our process for this is the same. First, check for positive terms. Second, find our comparison series. And the limit comparison test is a little bit more forgiving. There's often a lot of series we could use, but just finding the easiest one to work with, or the first one we find to work with, is going to help get us in the right direction. So find some series to compare to, then determine if that comparison series converges or diverges. Determine convergence or divergence of comparison series. Once again, this is often going to be comparing to a geometric or p-series, meaning we'll know if it converges or diverges really easily, but we do need to state if it converges or diverges and why. So then 4, we run the test, and this time the test is our limit. And then 5, we make our conclusion. Before we take a look at our first example, there's a little bit of a but wait of, okay, we have these two series that have positive terms, and their limit is positive and finite, but is there anything we can do if the limit is either 0 or that limit is infinity? And yes, there are two special cases that we will address here. And that is if the limit happens to come out to be 0, and we know that the series Bn converges, then the series An also has to converge. So this is because of growth rates. If the limit of An over Bn is going to 0, that means Bn is growing faster. It's getting bigger at a faster rate, making it essentially a bigger sequence. And we know if the bigger sequence converges, or the series of the bigger sequence converges, then the series of the smaller sequence will also converge. And then we have a reverse special case, which is also by growth rates. If the limit of An over Bn equals infinity, and the series of Bn diverges, then again, this means that the sequence An is growing faster than the sequence of Bn. And if An is growing faster and Bn already itself diverges, then the bigger thing has to still diverge. So then the series An must also diverge. So we have two special cases that come up, and when we get those limits, we then have to look back and see, did all the other appropriate properties get met? Specifically, did the comparison series converge or did it diverge? Right, so taking a look at an example of this, we're going to go through these 5 steps. First, just mentally check, is this positive? And yes, n over 2n cubed minus 1 is bigger than 0 for n greater than or equal to 1. This is true because 2n cubed minus 1 is never smaller than 1. So that denominator is always positive. Step 2 is to find what we want to compare to. And this is going to work incredibly similarly to the direct comparison test, where we say, I want to compare to overall, what does this sequence look like? Or what does this series look like? So n equals 1 to infinity. Picking out the big things, we have n, and we have a 2n cubed. Simplifying that down, n equals 1 to infinity is 1 over n squared. We actually did a problem like this in the first video, where we compared to 1 over 2n squared. And when we compare to 1 over 2n squared, that is a p-series test, which converges because, or by p-series, with p equal to 2, which is bigger than 1. So we have our series that we're comparing to converges. So there is step 3. Step 4 is to run our test. So we want to take a look at the limit of an is the sequence or in series we want to know about. So we're going to do n over 2n cubed minus 1 all over. And then 1 over 2n squared is the one we found. So limit as n goes to infinity of this. Keep change flip gives us n over 2n cubed minus 1 times 2n squared over 1. This is the limit as n goes to infinity of 2n cubed over 2n cubed minus 1. This limit equals 1 by our rational limit properties. And so 1 is between 0 and infinity. 1 is positive and finite. This means that the series 1 over 2n squared and the series n over 2n cubed minus 1, they do the same thing. So, since they do the same thing, 1 over 2n squared converges. This means the series n equals 1 to infinity n over 2n cubed minus 1 converges by the limit comparison test, since the series 1 over 2n squared from n equals 1 to infinity converges. So there is our first example. If we were to have tried to use the direct comparison test on this, we would have actually gotten one of the cases that the direct comparison test fails. Because if we compare these two sequences, n over 2n cubed minus 1 and 1 over 2n cubed, or n over 2n cubed, if we compared those two, the bigger the denominator, the smaller the fraction, our inequality would go this way. But then we get that the small series converges. Right, this is the small series. And that is a case we don't know about. Remember, if our sequences are such that we have a bigger sequence that we don't know about, and the smaller sequence converges, the direct comparison test doesn't work. So this is a case where that direct comparison test would have failed, but the limit comparison test worked quite nicely. In the next video, we'll take a look at 3 more examples of using the limit comparison test as we finish the comparison test section.